Thank you very much. Okay. First of all, I would like to thank everybody, okay, for coming to this lunch. I would call it more like a conversation. So I would like to make it like a conversation, and then please, you can ask me questions as I go along through the presentation because I want it to be very informal. Okay, don't wait until the end. Okay, if you find something that interests you or something that kind of nag you a little bit, you can just interrupt and then ask the questions. And then the rest of the people can then come into the conversation. So today what I'm talking about will be on smart materials for better health and environment. What do we mean by smart materials? Smart material are material that can respond to changes in the environment or situations. Okay, so these are emerging line of research in developing new materials that can actually do more active intervention, okay, depending on what is happening on its surrounding. Okay, so I'll just give a very brief, I got my PhD degree in the US at University of Notre Dame. Currently, I had a joint appointment with the Chemical and Biomolecular Engineering and the Division of Environment. So most of my research is both curiosity driven and at the same time there's quite a bit of application. Okay, so we had currently around 11 patents and 8 of them are basically being commercialized. Okay, so there are about 7 billion reasons. Okay, just 2 weeks ago there are now 7 billion reasons why we need to think about health and environment. Okay, this is currently the population of the world. Okay, as the population become more crowded, as the earth become more crowded, this will become more and more important. Okay, so first I'm dividing the talk into 2 parts. First is the health, then the environment. Okay, so what I would like to do is just pick up 1 or 2 of my research in this area and then start a conversation. There are other research that I'm also working in. My focus is actually on materials, as I mentioned, smart material with different application, broad applications. So for the health side, I'm picking up 2 of my project. One is on the so-called smart antimicrobial. The other one on painless microneedles. Because both of the project had a little bit of back story about it, which I think would be of quite interest to everybody. Now, Hong Kong is not a stranger, okay, to outbreak. Since I returned to Hong Kong in '96, I'm experiencing every 5 years there's a major outbreak, okay, and each time there's an outbreak, there is a significant change in people's lifestyle and habit, okay. In 1996, okay, taikasik would kai. Correct. Everybody had to have live poultry. Okay, that is more or less a must. Okay, now rarely you can get any of that. 2003, prior to that, okay, 2 things, big major changes. Like before that, everybody will not wear a mask, and then there are no individual packaging for foods. Okay, typically that is the situation, and after that it changes again. Okay, so these are very big life-changing events. Okay, not only economic-wise but also in terms of human habit. And each year there's about 1 billion people getting sick of influenza, and I would be very honest. I get sick once a year of influenza, especially if you have a kid. Probably get it more than once a year. And then if it mutate, then the fatalities can be much higher, okay? And then in hospital nowadays, there are more and more emerging a drug-resistant bacteria because of the way that we use antibiotics. And the way that the number of antibiotics being discovered is actually limited, okay? So that is becoming a very important issue. So stopping disease transmission is therefore very critical for individual and community health. Now, this backstory for why I got into this field, because my background is not really in this field. It was back in 2004, okay, just after the SARS period, and we had an ITF grant that we were working with a company. And that company had a very good relationship with the city of Beijing. And at that time, city of Beijing had been announced that it's going to host the Olympic in 2008. And they were very concerned that SARS is going to be an annual event. So they basically assemble a panel of experts to come out with a potential solution if it is going to be an annual event, how to intervene, okay, on this problem. So what they come up with is an attributes, a series of attributes wherein the company then shared with me whether I'm interested in looking at this problem. Number one, any technology, they wanted it to be a coating material. It had to be simple and easy to use. It had to be rapid and effective. And then at that time, they were talking about 90% reduction of any type of microbial that come into contact with the surface, okay, within 30 minutes, okay, because they're doctor expert, that is what they mentioned. Now, one application minimum 30 days, because Olympics takes about 28 days. So that is the requirement that they had, okay? And then it had, the smart component is like they need to self-disinfect. Okay, places that get contaminated either by touch or by droplet, it had to be able to self-disinfect those areas very quickly, and if possible, also self-clean. And everything had to be, all ingredient and all component had to be US EPA or US FDA approved, okay? And simultaneously, one of the very important key factor that they wanted is that whatever coating that you come up with, nobody should notice it. It had to be very discreet. It had to be colorless, odorless, tactile-less. So this is quite a tough job. So when I took this project on, I didn't ask for any money because at that time I said, I don't know whether I can do that. Okay, but we'll look at it. It's an interesting problem for us. So I assembled a team of undergraduate students. We started with undergraduate student. I said, undergraduate student is very good researcher. Why? They don't know that it cannot be done. Okay, so that is what we do. We assembled them. We did literature search. We kind of like narrowed down what the material is. End of 2004, we come up with the first formulation that meet their expectations. So we deliver that. Unfortunately, 2005 there's no SARS. 2006 there's no SARS. So that is gone. But I'm very interested in it. So I keep on working on that, even though without any funding, okay, mostly through undergraduate and Master of Science student. So I sustain it. So now, today, okay, I get the funding. The first funding from the government is in 2009, just after the swine flu, okay, event. Okay, so that was when we got the funding. Then we can actually speed up the whole process. So we already did a lot of the background research, even though it's an undergraduate level. So one of the important issue when you're looking at the material that you potentially going to commercialize is that from the beginning, you already have to put in the cost of the materials. So however the technology that you're going to put in, you already need to factor in the cost. So the one way that we did is like we said, okay, we're going to make it using cosmetic method because it's easy to scale up. It's relatively cheap, okay, and then we can try to use this technology. So the anatomy of the system is like we use simple polymers. These polymers are actually something that you already found in some of the food additive, in some of the medical additives, in some of your contact lens cleaner. Okay, the material that we use are all FDA approved. Okay, we just assemble it in a different way. So the way that we say, okay, a similar piece of steel, you can either use it to make a bicycle or a spaceship. It's just like how you design it, how you employ it. It can be the same material, but the way that you actually use the material become very important. So in this case, the polymer have multiple functions. The way that we do it is like, number one, we don't want to have too many ingredients because they might have any cross reactions. So we wanted to minimize the ingredients so everything had the multiple function. We want it to be able to respond to the environment. So that is one of the issues that we're looking at. Formulation is sprayed on. Once it coats onto the surface, it will automatically form a film, okay? And then this film is transparent, odorless, and tactile-less. And in fact, after we deliver it, they told us, how do we know that the coating is there? Okay. So, okay, you have to make up your mind whether you want to know it's there or not, okay? So that is one thing. In fact, we come up with a method. It's a litmus paper test for them. So when they put it on the surface, there will be color change if the coating is there, okay? The spray-down formulation can kill, okay, inactivate viruses, bacteria, as well as a spore by 4 log, okay, 99.99% within 1 minute, okay. But once it forms a film, okay, the material need the biocide, okay, it has several killing components. The biocide had to come out, so it takes a little bit longer time, okay. So 99.9% within 1 minute for most bacteria. Viruses, 99% within 1 minute, and spores, 99% within 30 minutes, okay? So we're trying like Bacillus subtilis spore, surrogate for anthrax. We try fungal spores also. So it's long-lasting, as you can see. Like most disinfectant, what is the difference between this and other disinfectant is that disinfectant is very effective. I'm not saying that they are bad. But once you disinfect, okay, once it dry off, there's no residual activity. So the next person touching it will contaminate it, okay? But this one have a residual activity, and it also responds to contamination. So that is very important. So it can maintain the performance. So in this case, we tested it for an S. aureus up to 60 days, okay? So it's continuously have a performance, okay? And then the way that we also calculate how much is remaining, the main ingredient, the biocide, okay, is released only 20% of the total amount that is stored within 1 month. So by extrapolation, you can actually have it for at least 5 to 6 months in terms of effectiveness. And then at the same time, because a lot of time in most of the bactericidal thing like MAP or coating materials, they rely a lot on what we know as water breach, okay? They need the presence of moisture to pull out the biocide from the material in order for it to work. Now, this one is not, because the main ingredient, the biocide, is actually a gas, okay? So it doesn't need that. And it's very insensitive to any dirt, okay, on the surface. A lot of bactericidal surface, if you got soil, if you got blood on it, it's not going to work, okay? So this is as a gas phase, and it's a very selective, so it can actually travel, okay? Now, all this like grayish area here is where all the bacteria are growing. So we put a plate with this coating, but not in contact. We have a gap about 1 millimeter. So it will basically kill all the bacteria above it, so it will clear the zone. So up to 3 millimeter, it will do that. Of course, too far away, it will not work, okay? So that is one thing that is very important on this technology. It responds to touch. Area that you touch will basically disinfect by releasing 10 times more. So it can kill very, very quick. Disinfect by droplets, because like a lot of time people talk or sneeze or, you know, you will have droplet, okay? So this droplet will also trigger very rapid like disinfection of the materials. And it has self-cleaning, because one of the components have a detergent action, so it prevents the bacteria from adhering to the surface, and it also self-clean it. Okay, so this component is similar to the one that you use in contact lens. Okay, so that is one of the issue. So we did a field test starting January this year in 3 public hospitals in Hong Kong. Twin Mun Hospital, Princess Margaret, and Queen Elizabeth Hospital. In the Twin Mun Hospital, we done it in an unoccupied ward, okay, to test the safety, the process, and also the compatibility with different medical items. In Princess Margaret, we basically did all the multi-drug resistant organism, MDROs. These are like MRSA and other materials. In the Queen Elizabeth, we did it in the ICU, as well as in their orthopedics ward. And then this coming, yesterday, their infectious doctor, Dr. Dominic Chang, I think just make a press announcement to the press that that we would do it on the neurosurgical ward, wherein they just had a recent BRE outbreak. Okay, so that is where we would do the next phase of the study in the neurosurgical ward.